All right, continuing on in Unit 5, we're going to talk about electrolytes. Strong electrolytes, weak electrolytes, and non-electrolytes. Perhaps you've heard of electrolyte replenishment therapy. Sounds like an impressive therapy, right? Actually, you probably all have had some form of electrolyte replenishment therapy, and and that's just as simple as drinking Gatorade. So, electrolytes refer to ions. So, if you look at Gatorade, there's some sodium, there's some potassium, chloride, all these different ions that are dissolved in water. And so you're getting electrolytes by drinking Gatorade. Now, you could be dehydrated, your electrolyte balance is off, so you need replenishment. So that's why you reach to your Gatorade or Powerade or whatever brand you reach for. But we're going to go through what an electrolyte is. We're first going to talk about a strong electrolyte. So a strong electrolyte is something that ionizes completely in water. So if you remember, we talked about ions in Unit 2. Ions are charged species. So you have a cation or an anion. So if you have something that ionizes completely in water, this is going to be an ionic compound. So always ionic compounds. So when you put an ionic compound in water, it's going to break up into its component charges. For instance, sodium chloride. If you buy sodium chloride from the store, how do you buy it? Comes in like a cardboard container, solid, right? When you put it in water, it dissolves. So sodium chloride starts off as a solid, then you add water, and it breaks up into its ions. Now, you might think it dissolves. It does that because it's soluble, and then it forms ions. How do we know it forms ions? Because electricity can be conducted in this solution. So, let's see what happens when we take sodium chloride and put water. What would the charge on sodium be? Well, sodium forms what charge? +1. Chloride forms a -1 charge. So sodium chloride, when you put it into water, it will ionize. It ionizes by forming these ions. Another word for ionize is dissociate. So I'm going to put dissociate here. So it ionizes or dissociates. It's soluble. The way we know it's soluble is that it's dissolved in water, and we put the AQ there. AQ means aqueous, and it's soluble in water. Now the reason I go through this clarification, we will learn solubility rules coming up in Unit 5. So it's important to differentiate between soluble, something that dissolves, and something that ionizes. Sodium chloride does both. It's soluble, so that's why it gets the AQ by it, and it also ionizes. It forms those charges. So this would conduct electricity. So if you were going to drop your hairdryer into, you had 3 choices. You had sodium chloride dissolved in water. You had, let's say, acetic acid, which is a weak electrolyte. and then you had a non-electrolyte. You would want to choose the one that was a non-electrolyte because there aren't any charges around. It wouldn't conduct electricity. If you dropped your hairdryer in this solution of sodium chloride, electricity would be conducted. If you were standing in this, you would get electrocuted. Hopefully your GFCI outlet would click off and nothing would happen. But, just to give you an idea of what I mean when we're talking about ionize or dissociate. Now in lab, we have probes that can determine how much electricity is conducted. And it can tell you whether you're dealing with a strong electrolyte, a non-electrolyte, or a weak electrolyte. So, let's look at this next reaction that I have written. Solid aluminum nitrate. When you put that in water, what's going to happen? Well, aluminum nitrate, is it an ionic compound? Yes, it is an ionic compound. You have a metal to a polyatomic ion. Now, since you guys have been studying, reviewing for your final, you can probably tell me very quickly what the formula for aluminum nitrate is, right? All right, think about this for a second. Aluminum has a +3 charge, and nitrate is NO3 -1. So the formula for aluminum nitrate would be AlNO3, 3, and then salt. All right, so this is an ionic compound. When you put it in water, it's going to break apart. So it's going to break into its ions. It's soluble, so we'll get the AQ. The AQ. Now, I'm telling you it's soluble. We'll learn rules coming up later, so you won't have to rely on me. Now, what would the charge be on aluminum? Be +3, and then nitrate would be -1. Now, is this equation balanced? No, it's not balanced. I have one aluminum, one aluminum. On the left, I have 3 nitrates. On the right, I have 1 nitrate. So I need to put a 3 in front of it. So, strong electrolytes are always ionic compounds. They ionize completely in water. They're going to conduct electricity readily. Weak electrolytes ionize to a small extent. %10 or less. Weak electrolytes most often contain polar covalent bonds. So, with weak electrolytes, the way you know they're weak electrolytes is because this arrow is used. Kind of the I can't really make up my mind arrow. Sometimes I go this way, sometimes I go that way. I'm just not quite sure. This is the arrow that's used for weak electrolytes. So acetic acid is a weak electrolyte, and you guys learned what the structure of acetic acid was in Unit 4. Acetic acid is a carboxylic acid, acet. It has 1 or 2 carbons. Acet is 2 carbons, right? So it's a 2-carbon carboxylic acid. So let's draw this out. 2-carbon carboxylic acid. And remember, the functional group in a carboxylic acid is a C double bond O, OH, and then we'll just fill in our hydrogen over here. Now, with carboxylic acids, and we'll talk about this later on in Unit 5, what comes off, or what ionizes, is this hydrogen right here. That's what makes it an acid, and we'll talk about acids and bases coming up too. So, when you put acetic acid in water, it's a weak electrolyte. It ionizes a small extent, so it conducts some electricity, not as much as a strong electrolyte, but this is what you get happening. O- plus H+. So this is aqueous and this is aqueous. So at any given time, you could have 5% of these ionized and then 95% here. So The 95% would be molecules, and then the 5% would be ions. Whereas with ionic compounds, at any given time, you have 100% ions. You don't have any molecules with strong electrolytes. So with weak electrolytes, you have a lot of molecules and a few ions. Strong electrolytes, you have all ions. Now, what do you think about non-electrolytes? Non-electrolytes, you have no ions in solution. So if you have no ions in solution, then you have all molecules. So, sugar, for instance, is an example of a non-electrolyte. Now, if you've ever had sugar water, soda pretty much is sugar water, right? You know that sugar dissolves in water. What you don't know is that sugar doesn't conduct electricity because it's a non-electrolyte. So what changes? Well, there aren't any ions produced because this is a non-electrolyte, but we do see the change from solid to aqueous. This means that it's soluble, remember? And you know that sugar dissolves in water. You know, I have some friends who love sweet tea, and they just take their unsweetened tea and they just dump gobs and gobs of sugar into it. So sugar will dissolve to a certain extent, and then you get solid at the bottom, and that's how my friends prefer to drink their tea, which is just crazy to me. But you know that sugar goes from solid to liquid. So when you put it in water, it's soluble, but it does not form a charge, doesn't form any ions. That's why it's a non-electrolyte. So sugar is an example of a non-electrolyte. It's all molecules, all molecules. Now, in the medical profession, it is very useful to quantify how many units of charge we have. For instance, if you have a patient who is very dehydrated or definitely needs some electrolytes as soon as possible, you would want to make sure that you're delivering the correct number of ions, charges, and it's easiest, instead of saying ions, to say equivalents. Now, equivalent is the amount of positive or negative ion that supplies 1 mole of charge. So it's the amount of positive or negative ion that supplies 1 mole of charge. So it's a lot easier to say equivalence as opposed to has 50 cations, 50 anions, so many chloride anions, so many sodium ions, cations. You know, it's just a lot easier to say equivalents. So frequently, milliequivalents are used. 1 equivalent is equal to how many milliequivalents? Well, you guys learned about your unit prefixes way back in Unit 1. 1 equivalent is 1,000 milliequivalents. And equivalent, the abbreviation is E, capital E, lowercase q. So, I'm sure you're thinking, what is she talking about at this point? I'm not really following her. It's not as difficult as it may seem right now. We'll go through some examples. So sodium ion. What charge does it have? +1. So that means that the number of equivalents in 1 mole of sodium ion would be 1. So because you have Na plus 1. So 1 mole of sodium ion produces 1 equivalent. Calcium has a plus 2 charge. So in 1 mole of calcium ion, you have 2 equivalents. Iron 3 ion has a plus 3 charge, so it produces 3 equivalents per 1 mole. Chloride ion, -1, produces 1 equivalent. So this is the absolute value. You don't have to worry about the positive or the negative. Which is nice. Now sulfate ion is SO4 minus 2. I'm sure you guys remember this, right? So the charge is -2. The number of equivalents that would be produced would be 2. So these are conversion factors. 1 mole of calcium ion is 2 equivalents of calcium ion. 1 mole of sulfate ion is 2 equivalents of sulfate ion. So if I asked you how many equivalents are in 6 grams of magnesium ion, I would have to start off with 6 grams of magnesium, and I would have to convert grams to moles. So I would get that off the periodic table. The molar mass is 24.31 grams per 1 mole of magnesium. So now I've gotten it to moles of magnesium. So for moles of magnesium, I can get 2 equivalents. So in 1 mole of magnesium, I have 2 equivalents. So 6 times 2 divided by 24.31, end up with 2 sig figs. You get 0.49 equivalents of magnesium ion. All right, so another question. How many grams of sulfate ion are present in 3 equivalents of sulfate ion? So, all right, 3. So my starting quantity is this. So I go from equivalents, so equivalents to moles to grams. That's kind of my conversion roadmap. So 3.00 equivalents. So 1 and mole always go together. So 1 mole of sulfate ion gives you 2 equivalents. So from there, I can go from grams to moles. Need to calculate the molar mass. So sulfur is 32.06, oxygen 16. So 16 times 4 plus 32.06 gives you a molar mass of 96.06 grams in 1 mole. 3 divided by 2 times 96.06 gives you 144 grams of sulfate ion. So, when you're asked to work problems involving equivalents, 1 always goes with mole. The ion charge gives you the number of equivalents. Also remember that 1 equivalent equals 1,000 milliequivalents. Alright, so moving on, we're going to talk about solubility. And I've kind of referred to this in previous lectures and in this lecture. Solubility is defined as the maximum amount of substance that will dissolve in a given amount of solvent at a specific temperature. The maximum amount of substance that will dissolve in a given amount of solvent at a specific temperature. So for instance, sodium chloride could have a solubility of 344 grams of sodium chloride per 100 grams of water. That would be the solubility. Now, there are different ways, different situations that you can come about when you're dealing with solutions. You can have unsaturated solutions, saturated solutions, supersaturated solutions. So an unsaturated solution is a solution which can dissolve more solute. So for instance, if I had a solution which can dissolve more solute, is unsaturated. So if I had, let's say I had 100 grams of sodium chloride in 100 grams of water, given the solubility above, I can definitely dissolve more sodium chloride. In fact, I can dissolve 244 more grams of sodium chloride in that amount of water. So that's an unsaturated solution. So it's not fully saturated. Now, a saturated solution, on the other hand, is a solution which contains the maximum amount of solute. So an example of this, but EX example would be 344 grams of sodium chloride per 100 grams of water. So I have the maximum amount of solute that that water can contain, so it's saturated. Now, a supersaturated solution, this is unstable, by the way. So it's not going to stay like this forever. This is a solution that contains more solute than the saturated amount. So a solution that contains more solute than the saturated amount. So my example, 350 grams of sodium chloride per 100 grams of water. So a lot of times supersaturated solutions are created by heating up your solution and then being able to add more solute, because these solubilities are specific for temperatures. So generally, for a solid dissolved in a liquid, as temperature increases, solubility increases. And for a gas dissolved in a liquid, as temperature increases, solubility decreases. And if that's hard for you to think about with a gas, for a gas dissolved in a liquid, as temperature increases, solubility decreases. Think about soda. Would you rather leave your soda in a nice cool refrigerator if it's already open versus outside when it's 100 degrees? You know, it's going to go flat a lot faster if it's outside because the gas is not as soluble. So we talked about unsaturated, saturated, and supersaturated. So these terms describe solutions. I'm going to get another sheet of paper to do a practice problem involving these terms. So let's say I have an unknown compound. An unknown compound. I'll just call it A, has a solubility of 238 grams per 100 grams of water. And I'll put at 25 degrees Celsius, which is room temperature. So an unknown compound, A, has a solubility of 238 grams per 100 grams of water at 25 degrees Celsius. I'm going to give you some different scenarios. So let's say we were able to dissolve 65 grams of compound A in 50 grams of water. Is it unsaturated, saturated, or supersaturated? All right, be careful on this problem. 65 grams of compound A and 50 grams of water. We are halving the amount of water. So we have to half the solubility. So and 50 grams of water, 238 divided by 2 gives you 119. So if you had 119 grams and 50 grams of water, that would be saturated. So this is unsaturated. Okay, so let me give you another scenario. Let's say you have 478 grams of compound A and 200 grams of water. Unsaturated, saturated, or supersaturated. All right, so, well, let's do, so 200 grams of water, 238 times 2, you get 476 grams. So 478, so it's not, the green number is saturated. So because it's 478, this would be supersaturated. So I wanted to go through this example. Some of your homework problems have different volumes. They either half the solvent or double the solvent. So just be on your toes. You know, make sure you do the same to the solubility and then compare. A lot of students just have a tendency not to say, oh, well, it's half as much. Get tricked by that. So the lab that you can really cover now for this week of labs, work on lab number 19. This is a lab that can be done all outside of lab, but it deals with the concepts of saturated, unsaturated, and supersaturated. So I will stop here for this lecture. The next lecture, we're going to get into the solubility rules, which are fun. I like them. I still know my solubility rules, but I get to say them every semester. So we cover a lot of material. Make sure you go over these definitions. Make sure you work on your homework problems. Work on lab 19. Until next time.